In this video, you're going to uncover one of the most misunderstood ideas in science, the way electricity actually works. We often think of electricity as electrons racing through wires at light speed. But in reality, individual electrons move at a snail's pace, just about a millimeter per second. Think of a kitchen faucet. When you turn it on, water appears instantly, not because one drop traveled the whole distance, but because the pipes were already full. Electricity is similar. It's a pressure wave of energy that travels through the circuit almost instantly, even while the electrons themselves barely crawl along. As Richard Feynman taught, the simple analogies we learn in school often hide a much deeper, more fascinating reality about electromagnetic fields. To dive deeper into the hidden principles of technology, subscribe and hit the bell icon. Let's keep exploring together. The class had learned to think of electricity as something moving through wires like a fluid through tubes. That mental picture is convenient, but it hides the deeper reality. So Feynman picked up his chalk and drew a simple circuit on the board, a battery, a wire, and a light bulb. Then he asked the class a new question. When you connect this circuit, what actually happens? Students offered the familiar answers. Electrons flow, current moves, energy travels through the wire. All of those statements were technically correct in some sense. But according to Feynman, they were missing the most important part of the story. He paused for a moment and then explained something that sounded strange at first. The energy that powers the light bulb does not actually move through the wire itself. Instead, it travels through the electromagnetic field that exists in the space around the wire. The classroom reacted immediately. Several students protested at once. The idea sounded impossible. One student spoke up quickly and asked the question everyone else was thinking. If the energy isn't inside the wire, then what exactly is the wire for? Feynman raised his hand to calm the room. He understood why the explanation felt strange. Most people imagine electricity as a substance moving through metal, almost like a stream flowing through a channel. But the real picture is more subtle. The wire is not simply a pipe carrying energy. Instead, it acts more like a guide that shapes and directs the electromagnetic field surrounding it. He compared it to a pipe carrying water, but with an important twist. Imagine that the water is not flowing inside the pipe at all, but along the outside surface. The pipe still determines the path the water follows, even though the water itself is not contained within it. In a similar way, the wire in an electrical circuit organizes the electromagnetic field so that energy travels in a controlled path from the power source to the device using that energy. Another student raised his hand. So the electrons in the wire don't matter? They matter a great deal, Feynman answered. Without them, the system would not work at all. But they are not the main carriers of energy the way people often imagine. Instead, their movement creates the electromagnetic field that actually transports the energy. He returned to the board and drew another diagram to explain the idea. Inside a conductor, electrons are already present throughout the entire length of the wire. They do move when a circuit is completed, but their motion is extremely slow. What matters more is that moving charges generate electromagnetic fields that extend outward into the space around the conductor. These fields spread through the surrounding space and carry energy with them. When a device like a light bulb is connected to the circuit, that energy arrives through the field and is delivered to the bulb almost instantly. This explanation addressed the puzzle that had confused the student earlier. When someone flips a light switch, the bulb does not wait for electrons to travel all the way from the switch to the filament. Instead, the change in the electromagnetic field spreads through the circuit at nearly the speed of light. That signal tells electrons everywhere in the wire to begin moving together. Feynman used a simple analogy. Imagine a long train. When the locomotive moves, the cars behind it shift almost immediately. Electrons in a wire behave like those train cars. They are already distributed throughout the conductor, interacting with their neighbors. But electrons don't carry the bulk of the energy. That energy flows through the electromagnetic field surrounding the wire. If energy is in the field, why use wires? Because electromagnetic fields spread out. The wire keeps the field focused, preventing energy loss. The signal travels close to the speed of light, while the actual drift of electrons is just a millimeter per second. This explains why devices respond instantly. The energy transfer happens through the field, not the slow movement of charges. The electrons create the field, but it's the field itself that carries the power through space. Amazing, isn't it? He paused to let the idea settle. What had started as a simple question was turning into a deeper lesson about the nature of electricity. Feynman then asked the class an important question. Why does this distinction matter? Misunderstanding the real mechanism can lead to serious problems. If you ignore electromagnetic fields, you might create inefficient or even dangerous systems. He pulled out a thick power cable. "Look at this," he said. "Thicker wires aren't just for resistance. The field around them needs space to behave properly." He held up a small battery next. What does a battery actually store? No, not electricity. A battery stores chemical energy. It doesn't push electrons like a pump pushes water. It creates conditions for an electromagnetic field to carry energy to your device. If energy travels through the field, why not power a bulb wirelessly? Because without a guided path, those fields spread out and weaken too quickly. By the time they reach the bulb, they are far too weak to provide useful energy. Curiosity is the key to understanding. The wire provides the structure that directs the field along a predictable path. It shapes the electromagnetic energy. Feynman drew diagrams showing wires bending and branching. Circuit design is actually about shaping patterns of electromagnetic fields. Every bend, every junction, every resistor changes how those fields behave. The layout determines how efficiently energy moves. Radio antennas work on the same principle. They are designed to launch those fields into open space. Even household wiring follows specific standards because those choices influence how electromagnetic fields behave. One student asked, "So everything we learned was wrong?" Feynman replied, "Not wrong, just simplified." The most common misconception is that electricity flows like water through pipes. It's a useful model, but it's misleading. In reality, energy exists in the field surrounding the conductor. The electrons merely respond to that field. Batteries don't store electricity. They store chemical energy, creating a potential difference that produces the field. Light switches don't physically block a substance. They break the circuit, changing the pattern of the electromagnetic field. Electricity is not a substance. It is a process. It is the behavior of the fields themselves. He explained that electrical systems work because of a coordinated interaction between moving charges and electromagnetic fields. The charges respond to the fields, and the fields guide the energy through space. Together, they create the phenomena we observe as electric power. One of the students raised a new question. If the deeper explanation is so different from the simplified one, why do we teach the simpler version first? Feynman answered calmly, because the complete explanation requires advanced mathematics and physics. Electromagnetic field theory involves concepts that are difficult to understand without years of study. For many practical situations, the simplified model works well enough. However, he warned that engineers who rely only on simplified explanations can struggle when they encounter complex systems. Understanding the role of fields becomes essential when designing advanced electronics, communication systems, or power networks. To demonstrate why the deeper model matters, Feynman proposed a thought experiment. Imagine two wires running parallel to each other with a small distance between them. One of the wires carries electric current. The question is whether the second wire experiences any effect. Most of the students initially believed it would not. If electricity flows only inside the first wire, why should the second wire notice anything? Feynman explained that the current in the first wire generates a magnetic field that spreads into the surrounding space. The second wire sits within that field. If current flows through both wires, the magnetic fields interact and produce a force between them. This phenomenon is known as the magnetic force between conductors. It explains why electrical wires can vibrate when large currents pass through them. It also forms the operating principle behind transformers, electric motors, and many other devices. Without understanding electromagnetic fields, these technologies would be impossible to design properly. Feynman then introduced another example that affects everyday life: long-distance power transmission. Electric power plants often generate electricity at very high voltages before sending it through transmission lines that stretch across entire regions. One student answered the common explanation: higher voltage reduces energy loss. That's correct, Feynman said, but let's understand why. If energy traveled purely through the wire itself, the advantage of high voltage might not seem obvious. But when we think in terms of electromagnetic fields, the reason becomes clearer. Higher voltage allows the same amount of power to be transmitted with lower electric current. Lower current produces weaker electromagnetic fields close to the conductor and reduces the energy lost as heat due to electrical resistance. As a result, more energy reaches its destination efficiently. Engineers who understand the role of electromagnetic fields can design transmission systems that waste less power and operate more safely. Those who rely only on memorized formulas may still solve problems, but they will not truly understand why the formulas work. Feynman paused for a moment and returned to the original example that had started the entire discussion, the simple act of flipping a light switch. What seems like an ordinary everyday action is actually the result of a complex and elegant interaction between charges, fields, and energy moving through space. When Feynman returned to the example of the light switch, the class began to look at something familiar in a completely new way. The simple act of turning on a light had always seemed straightforward. Flip the switch, electricity flows, and the bulb lights up. But before the switch is flipped, the circuit is opened. The battery maintains a voltage difference, creating a field confined near its terminals. The moment the switch closes, everything changes. The field extends through the entire network of wires at nearly the speed of light. Instead of a single electron traveling from the switch to the bulb, electrons all along the wire begin drifting almost simultaneously. However, the electrons themselves barely travel any distance. Their motion remains slow and limited. What moves quickly is the electromagnetic field that carries energy through the space surrounding the wire. This energy reaches the light bulb almost instantly, heating the filament until it becomes hot enough to emit visible light. In the accurate picture, the energy arrives through the field surrounding the circuit, not the electrons themselves. At an even deeper level, physics describes this using quantum mechanics, where fields are made of tiny packets of energy called photons. Feynman's lesson teaches us that even the simplest act hides a world of incredible complexity, a deeper mystery for another time. Electrons are more than simple particles. In quantum mechanics, they are described by wave functions. Feynman explained that understanding physics requires a layered approach, moving from simple analogies to complex fields. For beginners, electricity flows like water through pipes, helping us grasp basic circuits. Engineers, however, use electromagnetic field models for deeper insight into complex systems. The important lesson Feynman taught is not to assume our first explanation is the complete truth. Scientific understanding improves over time as better models are developed. We uncover truth one deeper explanation at a time.